Hello everyone, I'm Rui Xingguo from China University of Geosciences. It's my pleasure to introduce my work, BaPa, a novel approach of improving load balance in parallel matrix factorization for recommender systems. The outline of this video is as follows. I will start at background and motivation. Matrix factorization is widely used in recommender systems. It is to factorize a matrix R into U and V. R is usually sparse. Most of its entries are mixed. We call each observed entry in R a non-zero. The product of U and Vt is an approximation of R which recovers R by filling the missing entries. Matrix factorization can be regarded as a machine learning problem. We can define the loss function like this. This loss function means we need to find suitable U and V to minimize the square loss of non-zeros. We can solve the loss function using machine learning methods such as SGD and CCD. In real-world application, the datasets can usually be large. Training these datasets, serial algorithm is usually slow, so parallel computing is a common approach to accelerate training. DSGD and CCD++ are two parallel matrix factorization algorithms. Both of them partition a matrix into n by n blocks and use n tasks to implement parallel computing. Here is an illustration of CCD++ and DSGD. We suppose that n is 3. In each iteration, CCD++ has 2 steps. In step 1, each task computes a law block, and these tasks are executed in parallel. In step 2, each task computes a column block. As for DSGD, it has 3 steps. In each step, each task computes a subblock. These subblocks are disjoint. Any 2 of them are not in the same row or same column. In each step, all tasks are implemented in synchronous parallel computing, which means the first finished task must wait until the last task to finish, then all tasks can go to the next step. An issue of DSGD and CCD++ is that they use equal-sized partitioning, which causes load imbalance problem. Here is an illustration of equal-sized partitioning. We partition the law indexes of a matrix into equal-sized segments, so as the column indexes. Therefore, each law block or column block or subblock has the same size. However, the number of non-zeros in them is different. This is how load imbalance was caused. The load balance of CCD++ and DSGD depends on different blocks. For CCD++, its load imbalance depends on the law blocks and the column blocks. For DSGD, its load balance depends on the subblocks. Since we know a block's computation time is proportional to the number of non-zeros it contains, and the runtime of each step depends on the block containing most non-zeros. Therefore, load imbalance will cause the task waiting time to be long and lowers down the parallel efficiency. To improve the speed up of DSGD and CCD++, we need to address the load imbalance problem. For CCD++, we need to balance the non-zeros in row blocks and column blocks. For DSGD, we need to balance the non-zeros in sub-blocks. Our contributions are as follows. First, we propose a novel partitioning method, balanced partitioning, or BaPa, which proves the balance of non-zeros in sub-blocks can be achieved by balancing the non-zeros in row blocks and column blocks. Second, we propose imbalance degree model, which is an estimation method to predict the speed up promotion by changing the partition method from SPA to BaPa. Now we introduce balanced partitioning. We first introduce how balanced partitioning is performed. We adjust the segments of rows and columns to achieve balanced partitioning. Our goal is to force the non-zeros evenly distributed among row blocks and column blocks. This can be regarded as a chance-on-chance partitioning problem, which is a one-dimensional partition problem, and it is also NP-hard, which means we can hardly find an optimal solution. But using some algorithms such as greedy algorithm, we can find some suboptimal solutions. Once we achieve the balance of non-zeros in row blocks and column blocks, the non-zeros in sub-blocks can be balanced. We use variance to measure the load balance degree of row blocks, column blocks, and sub-blocks. First, let x, y, t be the random variables of the number of non-zeros in row blocks, column blocks, and sub-blocks respectively. Then, let dx, dy, dt be the variance of x, y, t respectively. A larger variance means the load is more imbalanced. Then, in mathematical language, BaPa can be interpreted as follows. dt can be reduced by reducing dx and dy simultaneously. We use a theorem to prove the correctness of BaPa. Let supremum dt be the upper bound of dt and infimum dt be the lower bound of dt. Then supremum dt and infimum dt can be expressed like this. The theorem shows that both supremum dt and infimum dt depends on dx and dy. If we reduce dx and dy simultaneously, then both supremum dt and infimum dt will be reduced, which limits the range of dt and causes dt to decrease. However, the theory has a problem. Let's see through a corollary from the theorem. When dx equals to dy equals to 0, dt ranges between 0 and sum squared times n minus 1 divided by n to the fourth. 0 is the lower bound of dt and another is the upper bound of dt. This means even we have dx equals to dy equals to 0, the theorem cannot guarantee that dt equals to 0. It still ranges between its lower bound and upper bound. Whether dt is close to a lower bound or upper bound depends on the distribution of non-zeros. Let's see through two extreme cases. In the left case, each subblock has the same number of non-zeros, which is equals to sum divided by n squared. In this case, dt reaches its lower bound. In the right case, there are n blocks. Any two of them are not in the same row or same column, and each block has sum divided by n blocks. In this case, dt reaches its upper bound. Therefore, the theorem cannot explain whether dt is closer to its upper bound or lower bound, so we need to explain this through an experiment. In this experiment, we test the changes of supremum dt, infimum dt, and dt with dx on the three fixed dy respectively. In each figure, the x-axis represents dx, the y-axis represents dt, the red line represents supremum dt, which is a theoretical upper bound. The blue line represents infimum dt, which is a theoretical lower bound. The green line is the real value of dt, which is carried out by experiment. The result shows that the green line is closer to the blue line when dx and dy are small, which means dt is usually closer to its lower bound when dx and dy are small. In this experiment, we evaluate the speed up of SPA and BaPa for DSGD and CCD++. We implement parallel computing with MPI using up to 1,535 cores. The experiment result shows that when using BaPa, DSGD and CCD++ can achieve higher speed up than using SPA in most cases. Now we introduce imbalanced degree model. We may wonder, by changing the partition method from SPA to BaPa, how much speed up promotion can we receive? Imbalanced degree model is a tool we propose to estimate this promotion. We explain imbalanced degree model through a theorem. Let S be the proportion of increased speed up. S is defined as the ratio of speed up Bn to speed up En. Speed up Bn is the speed up of BaPa under n tasks. Speed up En is the speed up of SPA under n tasks. We define P as the imbalanced degree. The P of DSGD and CCD++ are different. We respectively define them as follows. Then the relationship of S and P is S approximately equals to 1 plus P. Note that S is the exact speed up promotion obtained by experiment, and 1 plus P is a theoretical estimation of S we proposed. In this experiment, we evaluate the accuracy of imbalanced degree model by comparing S and 1 plus P for DSGD and CCD++. The experiment result shows that the gap between S and 1 plus P is small and usually lower than 1. This proves that our estimation is accurate. Our works are concluded as follows. First, balanced partitioning can effectively alleviate load imbalance problem and enhance the speed up of DSGD and CCD++. Second, imbalanced degree model can roughly predict the promoted speed up of changing the partition method from SPA to BaPa with only a few computations. Please check out our full paper for more details. Our source code has been uploaded to GitHub, and you can visit them through the two links. If you have any question, feel free to contact me through this email. Thank you so much.